nonmetals paired with metals. That's a metal. That's a nonmetal. So that's one thing that you look at. Metals are always, for our purposes, the compounds we see, metals will always indicate the ionic compounds. Because metals, when they make compounds, unless they're working with other metals, in our case, are generally making ionic compounds. So that's one way that we can think about it. The other thing you can look for is the polyatomic ions from the list that we talked about last time. So if you see one of those 7 parts in a compound, in a formula, then you know that that's going to be also an ionic compound. Just looking for those. Because if you remember, if we see something like ammonium nitrate like this, that doesn't have any metals in it. So that metal rule doesn't help us here. So we look for the polyatomic ions that we know, ammonium and nitrate. So let's write those down. So look for metals, or look for the polyatomic ions, which, speaking of polyatomic ions, make sure that you're working on those if you don't know them already. Yeah?
So if it's metals together, it's not ionic?
If it's just metals by itself, right. But we're not going to see those kinds of compounds in this class, really. So, and metals can make covalent bonds too, which is the other side of this that we'll talk more about next week. But again, we're not going to worry too much about that in this class. So these rules work for us. All right, so now we know they're ionic compounds, and that tells us that we can come up with names following the rules that we've already talked about, where we name based on the names of the ions and possibly the charge for the ion if necessary. So let's look at the difference between these two. The one on the left, the metal is calcium. The one on the right, the metal is zirconium. What is the difference in naming based on those two? Like, what are those two? What's going to be different about those two when we write the name of the compound?
You need a stable charge for the.
Yeah, why?
Because it's chain.
Right. So we talked a while ago about how, and it was on the quiz, about how certain groups always have the same charge all the time. Like 1A is always +1 and 2A is always +2. And there's a few groups where that's the case, but everything else in the middle has to be specified what the charge is because it's variable. You have different ones. So calcium, Ca, is in group 2. That we know always has the same charge. And so that charge doesn't make it into the name. So if that's the case, since calcium is always +2, that means that our name does not need to include the charge because we always know what it is. If you say calcium, you know it's got to be +2, so there's no need to specify it. So our name can simply be what? Yeah, calcium carbonate. That's it. So those are the easier ones to know. The other thing you needed to know here, of course, is that CO3 is carbonate. You would know once you have that list of polyatomic ions memorized. All right, let's move over to the next one then. So we can still write down part of the name just by looking up the names of the ions, which is zirconium, and remember that in monoatomic ions, we chop off the end of the name and we change it to "ide" for the anion. So instead of chlorine, it becomes chloride. And most of those you'll just get used to with practice, like Oxygen becomes oxides, sulfur becomes sulfide, phosphorus becomes phosphide, nitride, so on. So that's good so far, but as we just talked about, this isn't really a complete name because there could be different zirconium chlorides depending on the charge on zirconium. So for this particular zirconium chloride, give myself a little bit more room, we need to know what the charge on zirconium is. And so for this one, for this example, what is the charge on zirconium?
4.
4 plus 4, because, well, how did you know that? Yeah, and what's the charge on chloride? -1. So we know that chloride is -1, and there's 4 of them. So that means that the zirconium must be +4 to balance that out, because the overall compound has to be neutral, so +4 -4. All right, so we'd write a Roman numeral 4 there, and that would be our correct complete name. We're good? All right, let's try some more. Keep trying this time. All right, try these 3 on your own, and then we'll look at them together. If you need a periodic table for reference, they're at the usual place, or you can look it up on All right. As usual, once you see your names, turn to the people around you and see if your names match up with theirs. Remember that the point is to learn about what you've done, so if it's not complete or something, that's fine. Just share what you've done and talk about it. Talk about any differences that you see, or if they're all the same, you're both right or you're both wrong.
What's the charge here? Or just one?
So maybe, for the ammonium, dye, or none of those things. All right, I saw a lot of good names here and some good conversations. So one strategy I saw that I think is good is if you don't know the whole name, write down what you do know. I saw some people writing, one half or the other half of the name, the cation or the anion, based on what they did know. And then you can kind of think about it, and if it's, an exam or something, you can always just throw in some guess and at least get partial credit, right? That's always good. But the other part of that strategy is if you write down the information you know, then you don't have to hold everything in your brain the whole time. And you can focus on, okay, I got this stuff down. So now what I really need to think about is the charge and which thing has which charge. So once you see parts of the name there, then you can just think about where you're going to put that charge in. So let's try that. On the first one, CO we can look up on the periodic table, and we know that that's cobalt. And then PO4 we know from the polyatomic ion list is phosphate. So you can write that down, and then you can think about, all right, is this one of those ones where I need the parentheses or not? You can keep that as a totally separate question. Put down your names, and then you think, okay, is it one or not? So is it one or not? Do I need the parentheses or not? Yes, you do. Why? Because we don't know the charge on cobalt until we figure it out, because cobalt's in the middle. So you look at the periodic table, cobalt's 27 right in the middle. There's no way we can predict that charge because it's not in one of those rows where we can predict the charge. And so we know that we've got to have the parentheses. Before we even figure out what's in there, we know we got to have parentheses, all right? So then at least you're part of the way there. And then maybe the hardest part is actually figuring out what goes in the parentheses. And to do that, we look at the charge on the anion, the part that we do know. So when we do that, we look at phosphate and we say, okay, well, I know that phosphate always has the same charge of -3. And as we talked about last time, there's no way of figuring that out. That's just a thing that you have to know for the class to be able to talk about these ions, is that that's a -3 ion. Once you know that, then you can look at the formula and say, well, the formula is made up of 1 CO and 1 PO4 ion, 1 cobalt ion and 1 phosphate ion. The phosphate ion is -3, so the cobalt ion must be +3 to balance that out, because everything has to balance to 0 in the overall compound. Then all that's left is to put that charge in the parentheses. So that's going to be cobalt 3 phosphate. See how that works? Okay, let's look at the next one. Yeah. The different way? Oh, okay. So you go back to this, where we were talking about the valence electrons, and any of those areas where we can use the valence electrons to figure out what the charge is going to be, those are the ones that have fixed absolute charges. So for our purposes for this naming, that ends up being group 1A, group 2A, and aluminum in group 3A. Everything else is kind of unknown. So it's really just those three. There's a couple exceptions to that that we're not going to get into in this class, that like ones that are in the middle, but that only have one charge, and so we don't use the parentheses, but we're not going to worry about that. So for your purposes, you can just say, okay, if it's out of this or aluminum, then we got to use the parentheses. All right, let's look at our next one. So now we have all non-metals. So this looks like maybe it could not be ionic. So what's the clue that this is actually an ionic compound?
Polyatomic.
Yeah, it's a polyatomic ion. It's got ammonium in it, NH4, right in that formula. So that's the clue that tells you that this one is actually ionic, even though it's made exclusively from non-metals. So this one is just going to be named ammonium oxide. Ammonium, we wouldn't put anything in parentheses because it's not a metal, it's not on the periodic table, and it always has the same charge. Always going to be +1. So then the last one, we used this one in lab on Tuesday. This is silver nitrate. We got silver, Ag, we've got nitrate. Yeah.
Why? Would it be silver?
Yeah, so nitrate is -1. So silver would have a charge of +1. Now this is one of those weird exceptions actually. So when you look up a bottle of silver nitrate, or if you noticed on Tuesday, it didn't have something in parentheses, and that's because silver is always +1. But for our purposes, just to not get confused, we'll just say, yeah, that you put the 1 there. Yeah.
So what does that mean, like, in the lab, if it's like silver 3 as opposed to silver 1? Like, what does that mean?
It means it's going to have a different formula, and it means it's going to do different stuff. So like the iron chloride that we used on Tuesday was iron 3 chloride, FeCl3. There's also iron 2 chloride, FeCl2. It's a totally different compound, does different stuff. So it is an important thing to see that and to recognize it and to write it as part of the name when there are different possibilities for that. Okay. All right, any other questions on how to do this? Okay, we're going to keep trying, but I want to add one more piece to it. There's another class of compounds that we'll name sometimes that we call covalent compounds. We will talk about what covalent exactly means next week when we talk about bonding and electronegativity and this kind of fun stuff. But for now, the most important marker of this is that covalent compounds are not made of ions. They're made of a different kind of interaction between atoms. So that means they don't have charged particles in them. They don't have +3s and -2s and all of that. They're combined in a different way. And you've probably heard of a lot of these. So things like CO2 or CO. Anybody heard of those compounds? Anybody know the names of those compounds? Carbon dioxide and carbon monoxide. Because covalent compounds aren't made of charged ions, there isn't the same requirement to balance out charges. So like, you know, if you have sodium and you have oxide, you always need 2 of the sodiums to balance the 1 oxide, because oxide is -2 and sodium is +1. But in covalent compounds, there can really be any number of any of the atoms that are involved. And so to clearly communicate which compound we're talking about, we need to be more specific than just saying the names of the 2 things. So does anybody know what's the difference between these, like physically? Is it important that they're different? No one. Yeah, one can kill you. Yeah. I mean, technically they can both kill you, but carbon dioxide is a waste product of respiration, and so it's something that we exhale as our body does its metabolism thing. If you are in an only carbon dioxide environment, that will kill you because you won't be getting oxygen. But carbon monoxide is usually much more dangerous because it can actually bind to oxygen receptors in your body and sort of slowly kill you without you knowing it, because it will just kind of make you sleepy and yeah. What causes it? Incomplete combustion primarily. So anytime something burns but doesn't quite have enough oxygen around, instead of when something burns with plenty of oxygen, like in a pure oxygen environment, or like in our Bunsen burners where we're feeding air into it, and you get that nice blue flame, you're burning up all the organic material, and you're turning it all into carbon dioxide. Ideally, carbon dioxide and water are the byproducts of combustion. If you don't have quite enough oxygen around, then some of the waste product is carbon monoxide. And so in real life, in actual whatever, every time you're burning something, you don't quite usually have enough oxygen around. Even the fuel itself can like prevent some oxygen from getting to it. So in things like grills, furnaces, all that, water heaters, all those things that are burning from gas or wood or whatever, chances are they're producing carbon monoxide. Another one is your car. Because your car is combusting the gasoline, it is producing carbon monoxide. Now your car has a catalytic converter, which helps to convert a lot of the carbon monoxide to carbon dioxide, but it's not perfect. So there's still a little bit of carbon monoxide coming out. So that's why things like grills and stoves stuff always say like not for use indoors, or you know, yeah, don't close the garage while your car is running, that kind of stuff. It is dangerous, and that's why you should always have carbon monoxide detectors, because you can't tell if it's around. You can't smell it, you can't see it, and you don't really know that you're being poisoned until it might be too late. Where are we going with that? Oh, right, the compounds. There was a story about somebody who actually caught themselves being poisoned by carbon monoxide because they were writing notes to themselves, but they didn't know, like they didn't remember writing the notes. And so they'd like wake up or just notice these notes that were clearly in their handwriting, but that they hadn't remembered writing. And they like posted online somewhere that they thought somebody was like messing with them or like what's going on. And one of the commenters in the thing on the article online was like, you might have carbon monoxide poisoning because you don't know what's going on and you're like clearly losing consciousness for times. So they got checked out and they were actually being poisoned by carbon monoxide. So yeah, so be careful with that. Get detectors, don't mess around with it. So anyway, with the names, clearly we need to know that these are different compounds. They're not ionic. Carbon isn't making a positive ion, and the oxide, even though we say it's oxide, it's not an anion either. It's not an oxide anion. So we distinguish covalent compounds by saying how many of each atom there are. So we say the first atom, carbon, and then we add a prefix to the second atom that tells us how many there are. And the prefixes are mono for 1 and di for 2, as we just used. Tri is 3. Tetra is 4. Penta is 5. And hexa is 6. And for most compounds, we don't need to go beyond 6. Other things you should know about covalent compound naming is that the first one doesn't get a prefix if there's just one of them. So if you think about it, really this should be monocarbon dioxide and monocarbon monoxide, but it's just been decided that you leave off that mono if there's just one of them. If there's more than one, then the first one can still get a prefix, such as N2O5, which would be dinitrogen pentoxide. Another kind of style thing you might notice is that when the second atom, like oxide, starts with a vowel, you leave off the A on the prefix, or you leave off this double vowel, the extra vowel. So this isn't monooxide, it's monoxide. And this isn't pentaoxide, it's pentoxide. That is not something that I would mark wrong if you wrote it on an exam, because it's not that big of a deal. But if you do look up names, or if you see the names, you'll notice that difference. When you work through the homework, I think it will make you like really do it properly, but it shouldn't like take off much credit or anything for it. The biggest issue with this type of naming is that everybody likes it. It's easier almost in a way than the last one, because you don't have to worry about these charges and balancing things out and figuring out what charge this is and what charge that is. You just say however many of each thing there is. So the biggest danger with this is using this style of naming on all the ones we already just did, because that wouldn't be correct. So you can't go back up to this one and call this diammonium oxide, or call where's another good one here? Or call this one strontium dinitrate. So that's not used in the ionic naming. And that's really, I think, probably the biggest error I see in these. So in order to use this scheme, you have to first recognize that your compound is purely a covalent compound and does not have ions in it. Then you can use this. All right, you ready to try some? All together? All right, I'm going to list some compounds, and I want you to try to name them. And then I will write a couple names, and I want you to write the formulas for the compounds. All right, try those 6. Yeah. Right.
Oh,
once again, if you got those done, check in with people around you and see how your names match up and where you might. I might talk about that.
The first like 4 were balancing. Were you writing down the names?
Not exactly. You're writing down the names.
Oh.
Yeah. Oh, okay. I said that again. So the first part you're supposed to write the names, the last 2 you're supposed to write down.
Oh my God. So it's like NO1 balance?
What?
Is NO1 a balance?
It is because it's a covalent compound. It's not ionic, so there's no ions there. There's no metals.
Wait, say it again? Because there's no metals on it?
Right, so it's not an ionic compound, it's a covalent compound. It's a different category.
So for gold,
Yeah.
we also
Alright.
We've been
Wait,
Yeah.
how come, wait, but the second one, where the chloride,
Right.
what it's called, it's a metal and non-metal.
Right, so the formula is given. All right, sounds like everybody had a chance to try these and talk about them, so let's look at them all together. All right, so sorry if the directions were a little bit confusing. The idea was the first 4, I gave you the formula and you write the name, and then the last 2, I gave you the name and you write the formula. Okay, so the very first one is kind of weird looking because it just says NO. So what is that? Yeah, so we're going to think about that as a, well, let's make ourselves a little flow chart. We can always think about these things the same way. So the first question we always ask is, ionic or covalent? I don't know what's going on here. Or covalent. So you ask yourself the question, is the compound ionic or is it covalent? Because depending on the answer, you're going to use different naming rules. If you determine that the compound is ionic, meaning it's made of positive and negative ions, cations and anions, then you're going to name it the way that we talked about first, which is like this, where you either decide if it has a parentheses or whatever. If it's covalent, then you're going to name it the way we talked about second, where you say how many of each there are using those prefixes.
So how do you know if it's, like, okay, so it's positive and negative is the ionic, and then no ions would be covalent, like, How do you know?
How do you know? Yeah, that's a good question. How do you know?
The ionic is or it can be the
Right. So either you look for a metal or you look for one of the polyatomic ions. And then you know it's ionic.
either it's a non-metal in a metal or a polyatomic.
Or a polyatomic ion with another polyatomic, or a metal with a polyatomic, or a whatever. Yeah. All right, so let's say we have two ways to go here. Once you've determined that it's covalent, there's no more choices to make. We're going to name using those prefixes like mono, di, etc. So you're going to say, you know, carbon dioxide or whatever, dinitrogen pentoxide, all those different ways that we just talked about. If it's ionic, we have one more choice to make. We have to decide whether or not to use the parentheses. And how do you determine that? Well, it is the charge, but how do you determine whether or not you should put parentheses with the charge in it? Yeah, if it's one of those metals, it's kind of in the middle of the periodic table or middle to the right. If it's anything but 1A, 2A, and aluminum, then it's got the parentheses. Otherwise, it doesn't. So if it has the parentheses, if it's one of those variable charge metals, then you name the metal with the charge in parentheses. No, it's not really the nonmetal. Let's just call it the anion. So the metal charge and then the anion. So, you know, cobalt-3 chloride, or what are the ones that we do? Cobalt-3 phosphate. If it's not a parentheses one, then we just say cation and the anion. So sodium chloride, or calcium oxide, or ammonium phosphate. We don't use the parentheses if it has a fixed charge, if that charge doesn't change. So let's practice this through the examples that you just worked on yourself, but now also using this. So we go NO, and our first question is ionic or covalent? So does this have a metal or some other kind of ion in it? It doesn't. It just has N and O. So that tells us that we're going down the covalent track here. And we're going to name it with the prefixes. So we would call this one nitrogen monoxide. Okay, how that works? Okay. Okay, next one over. Same thing. Let's look at the flow chart again. AuCl3, is that ionic or covalent? It's ionic. How do you know? Has a metal in it, has gold in it. All right, so is gold an ion that would have a different possible charges or always a fixed charge? Different possible charges because it's in the middle, right? So that tells us right now that we can write down most of the name, gold with parentheses, chloride. And then the last thing is to figure out what should be in those parentheses. And so we say, okay, well, chloride is a -1 ion, has a charge of -1. And there are 3 of them in this compound. So for gold to balance that out, we must have a +3 charge on gold. So this would be gold 3 chloride. So that works? Kind of. It's going to take some practice. We'll keep working on it. All right, next one. Same thing. Let's go back to the flow chart. Ionic or covalent? Mg3PO42. Ionic, yeah, that one's going to be ionic because, again, it has a metal and it has a polyatomic ion. Do we have to have parentheses for the ion? No, why not?
You know, charge for magnesium.
Yeah, we know the charge for magnesium. Is that what you're going to say? Yeah. So we know the charge for magnesium because it's in column 2A, so it always is a +2 charge. So once we know that, we don't have to do any calculating, right? We just write it down. It's just magnesium phosphate. The thing you did need to know on that is that PO4 is phosphate. So you needed to remember that from the list of polyatomic ions. Questions on that one? Problems with that? Okay. All right, next. SO3, ionic or covalent? That one's going to be covalent. How do you know? No metals or ions here. This one might be a little bit tricky at first because SO3 looks a lot like sulfate. So like when I've put this on exams and stuff before, some people will just write sulfate for the name. But it's not sulfate. How do you know it's not sulfate? One is it doesn't have a charge. If that were just an ion by itself, it would have to be charged. And then the other thing is sulfate is SO4 2-, not SO3. So that's why it's important to know those names and formulas of the polyatomic ions that we put in that list on Tuesday.
So for going back to the magnesium phosphate, if it is polyatomic, you don't need to do the parentheses.
Right. Well, no, that has nothing to do with the polyatomic. That's because magnesium never has a different charge. It's always +2. So you only need the parentheses when it's a metal that could possibly have different charges. All right, so back to SO3. This one's covalent, so we're going to name it covalently using those rules that we just talked about. So what would you call that? Sulfur trioxide, right? Notice how this formula, and this formula kind of look similar, but their names are very different. And that's because this is a covalent compound, whereas this is an ionic compound. In the ionic compound, we can't just use these convenient prefixes. It's more important to specify the charge on the metal. And so that's why we use the different naming scheme. All right, so on to the next two now, the last two. We've got some names, and we're going to draw some formulas from those names. So manganese 3 oxide. This goes back to now what we did earlier before we started talking about writing the names. We did the formulas first. So hopefully you have a little practice with this. Remember that the best way to do it, or the way that I would do it, is write down the ions, because the ions are given to you right in the name. So just write them down. Manganese 3 is Mn3+. So you look that up. You look up manganese on your periodic table, and you see that it's Mn. And the 3+ is given to you right in those parentheses. The parentheses are the charge. I saw not a lot, but I saw some people writing Mn with a subscript 3 and then O. That's not right here, because that 3 that's in the parentheses is not the subscript, it's the charge. It's not the little number on the bottom, it's the charge. All right, so then we can write oxide also. Oxide is O, and we know the charge on oxide because of its position in the periodic table. It's in column 6A, so what's its charge? -2, right? All right. So now what's left is to put those together into a compound. Balance the charges out. We've done this before. We've seen these where it's a 3 and a 2. And so you have to adjust both numbers to get them to match up. So that means we need 2 of these and 3 of these. And now we have 6+ and 6- overall. So then we write out the results of that, which is Mg, or whoops, not Mg. Sorry, Mn2O3. That's the formula for manganese 3 oxide. All right, and then the very last one, dioxygen difluoride. That one, once we see those prefixes, we don't have to worry about balancing anything at all. We just write down exactly what it tells us. So dioxygen difluoride means 2 oxygen, 2 fluorine. So that formula is just O2, F2. And with covalent compounds, remember, there's nothing charged there. So the formulas can look really weird, can look like they don't balance or atoms don't look like they should be with each other. That's fine, because that's just how those things happen to bond. All right, questions about these? Think you can do this? Getting there? All right, let's try a couple more. So same thing, I'm just going to throw some different ones in there, and you figure out either the name or the formula. Actually, wait. This one doesn't quite exist, but that's okay. We can pretend. All right, so you got 3 names to write and 2 formulas to write.
that the word on the second? The second ion? Yeah.
And only have the first one.
Gotcha.
All right, let's take a look at these. So I was looking around, these look pretty good. Looks like you're getting this, which is great. So the first one is, again, let's think through our flow chart. So it's ionic or covalent? For the first one? Ionic? Yeah, ionic because you got copper and sulfate, which are two ions. Are we going to use the parentheses or not? Yes, because copper is right in the middle, and so we need to say which kind of charge it has. So that's, okay, so that much is done. Copper, parentheses, sulfate. Okay, now let's figure out what goes in those parentheses. It says Cu with a subscript 2, so does that mean the 2 goes in the parentheses? No, right, because what goes in the parentheses? The charge. So to figure out the charge here, we look at the sulfate, and we know that sulfate is -2 from the list. If you haven't memorized that list yet, that's okay, but that's something to work on this weekend. And then the formula tells us that there are 2 copper ions. We can't change the formula. The formula is there. But what we can then say is, what does the charge on each copper have to be so that it balances out? And so the charge on each copper then must be +1 so that the 2 positives can balance out with the 2 minus over at sulfate. Once we figure that out, then we can put the charge in that parentheses. So this is copper 1 sulfate.
What charge in the parentheses?
No. Yeah.
The metals can never be negative.
Right. All right, next one. Ionic or covalent? Ionic, yeah, because again, we've got a metal and then a polyatomic ion. Sodium is our metal. Is sodium a metal that needs parentheses or no? No, because it's always the same. So then the name is just sodium sulfate. Good. All right, ClO, is that ionic or covalent? Covalent, right, because we've got no metals here, no other kinds of ions, so Cl and O. So then it's chlorine, not chloride because it's first. And that's just arbitrary in this case, but that's how the formula is written, chlorine first. So chlorine monoxide. Because it's covalent, we need to specify that there is 1 oxygen. If we just wrote chlorine oxide, that makes it sound ionic. That makes it sound like a chlorine ion and an oxide ion. So because it's covalent, we need to use those prefixes on the second atom. Okay, then the last two, we're going to write some formulas. So to write the formulas, we just write down each ion and then combine them so that the charges balance. So ammonium is NH4 and +1. Sulfate is SO4 and -2. So to combine those, we need 2 of the ammoniums so that we have 2+ and 2- overall. That compound then looks like, or that formula looks like this. Okay. Next one, same thing. We're going to write the ions and then figure out how to combine them. So iron is Fe, and the 2+, remember, we get from, not from the periodic table, but from the parentheses, from the number of parentheses. That tells us our charge on the ion. And the other ion here is fluoride, which is F, and we can use its position on the periodic table to know that what charge should it have? -1, right? So to bring those charges into balance, what do we need? Yeah, we need 2 of the Fs. So our overall formula is FeF2. All right, you think you can do this? I think you can do this. Okay, good. So next week, we will have our next quiz on Thursday. Not Tuesday, but Thursday. And a big part of it will be this stuff. So please get to work on this. Make sure you know those polyatomic ions. There's plenty of practice problems on in the practice exercises in Connect and in the book.
So there's a practice quiz up for it? Or?
There's not a practice quiz, but so there's the folder that says required homework, and then there's a folder that says extra practice homework. And there's one for the chapter in there. It's not only naming because there's the rest of the chapter that we haven't gotten to yet, but you can at least work through the naming ones also. All right, let me know if you have any questions over the weekend. I'll be in my office tomorrow morning, and I'll be answering questions whenever I get them. So happy studying.
Oh, once we